sure this thing's going. John Oxley is the economics tutor, just in general. And he has taken intermediate econ, and he's also pretty good with math and stuff. So he would be a resource for you if you have some questions too. So he, his contact information, I don't have it, you guys, most of you know, does everybody know John? Probably you might not. But he's listed in the tutor area. And I think he's holding some office hours, but he's mostly been doing it by appointment. So another thing, if a couple of you wanted to get together, if you were studying together, and you could go see John on a question together or something, whatever you guys want to do. Okay? All right. So today we get into the wonderful world of isoquants and isocosts. Did I give you that sheet last time?
6.
Yeah. All right. So let me start off before we even jump right into that worksheet with kind of the basics. So we're beginning our look at the theory of the firm. And what is the firm's objective? We talked about the consumer maximizing utility. What is the firm's objective? Maximize profits. Good. So maximize profits. Profits are equal to, what's our profit? General profit equation. Total revenue minus total cost. We could break that down. We've done this in principles a few different times. Price times quantity. So I sell 100 glasses of lemonade at $2 a piece. I've got $200 in the cash register. Minus, if I calculate my average total cost per unit times the quantity. Another way to look at the profit equation is the difference between price and average cost times the number of units that I produce. All right, we had a profit maximizing condition. In some ways similar to the utility maximizing condition, something that needed to hold in order to know that we're maximizing profits. What was that? Kind of a different way. How does a firm maximize profits? Okay, highest revenue with the lowest cost. And there was kind of a mathematical thing that we did similar to the marginal rate of substitution equal to the price ratio, but it dealt with the profit equation. How did we know that we couldn't do better at a particular quantity? So if we were potentially producing a quantity of 100 units, how could I be assured that 100 units was the profit maximizing quantity? What needed to be true at that quantity? Good. Marginal benefit equal marginal cost, or in particular, relevant to the equation, the benefit is the revenue. So marginal revenue equals marginal cost. So at the profit maximizing quantity, the solution to the profit maximizing problem, at Q star, the revenue generated by the last unit produced was equal to the cost of the last unit. Okay. That's kind of the general overview that should be in the back of your mind as we go through this material that looks at this problem slightly differently. So for chapter 6 material, we're going to think about the profit maximizing behavior of the firm a little bit differently. through a couple different ways. So we can think about cost subject to, should be similar language that we were used to from our utility chapter. We're going to minimize costs subject to an output constraint. For example, minimize cost subject to quantity being equal to 100 units. So I want to produce 100 erasers. What's the least costly way to do it? That's the idea. So we're going to minimize cost subject to quantity equal to 100. What is the variables that I have under my control as a company in characterizing the problem this way? I know that I want to produce 100 units and I want to minimize costs. What are my choice variables? What are the endogenous variables for the company? What are they choosing?
How they get those outputs.
Okay. So we have, let's make, we've got a single product firm, an eraser firm. So this is all they make, is erasers. So when you said, I think you said how, Adam, what do you mean by how? What is the actual choice that they're making in order to make 100 erasers?
The system they use.
Okay, the system that they use. And what's embodied in the system? Anybody jump in? Resources like what? Labor, materials, capital, right? So all the basic resources, but then we could start to get specific if we're thinking about erasers. There's this little fuzzy stuff here that we got to get from a fabric company or something, and we've got this foam thing that we need, styrofoam base that we get from another company, right? So we got those resources. We've got glue that this little guy sticks to. So we have some sort of adhesive that we're buying from somewhere else, right? So we're thinking about how we want to do that. Now, the materials price, you know, hopefully we can go and negotiate, but we're likely to be a price taker for some of those materials, right? We look it up, we might shop around, but if it's the styrofoam market, styrofoam goes in. Right? We are a price taker, we just buy that given whatever the market price is. So my point is we don't really have any influence necessarily on the price of resources. So we're going to take those as given to us. Similar to how we took prices as given in our beer and pizza with the consumer choosing outputs. Now, the thing that we might have a little more flexibility in is whether we have a more labor-intensive production process or a more capital-intensive production process. So you can imagine we could hire people with a glue gun to sit here and glue the thing and then put the fabric on and cut it with scissors. Or we could have a machine that runs through and automatically cuts the fabric to size, and then there's another machine on a conveyor belt, and it's got a little glue spraying system that goes psh, and then another machine goes bloop, and we go, right? So we can either have a labor-intensive production process as far as the how on the system of how we put it together, or we could have a capital-intensive production process. Which one do we choose? The one that costs the least, that's right. So that's kind of what we're facing here. So, so we're going to minimize costs subject to quantity being constrained at some amount by choosing an optimal quantity of resources. So let's look at that cost function. So what does the cost function look like? So total costs equals, put our equation goggles on. What is that thing going to look like? And let's just say that we've got two resources, labor and capital. We'll just leave it kind of simple, not get into fabric and glue and other things. So labor and capital. What does the cost function look like? If you were asked to calculate the total cost, what are some things you need? The price. So the price of what? Give me one of them. Labor. And what would we maybe call the price of labor? About a wage times the quantity of labor. So if I hired 10 hours of labor at 10 bucks an hour, I've spent 100 bucks. And what else? Okay, and how am I going to do that? Multiply it? Raise it to the square root of it? Or so to the square root of the number of capital? Add it, right? So we're just going to add it. I want to make sure we're going through the whole rigmarole. Okay, then I'll skip that one. All right, so plus the rental rate of capital, let's call it little r. Let me just try to stay consistent. This is your the problem I gave you. Oh shoot, I don't have my. I have to go get that. I can't. I just want to stay consistent. If it's big R or little r, I think it's for the rental rate. I think the first problem we were going to do has probably it on there. Or maybe the second problem. Just an attempt not to confuse you more than we need to. There it is. Yep, big R, big W. So the rental rate of capital times the quantity of capital. And that's it, if that's our only two resources. So there's your cost function. And how about if we graph this? Graphing this in LK space. Graphing this in LK space. So let's put labor on the horizontal axis, capital on the vertical axis. What does that function look like? What is it, what form does it take on? Squirming in their seats here. What should we do? If I've got K on the vertical axis, L down here, what would be a good idea to do to this function? Okay, how? What do you mean? Tell me in layman's terms how you're going to manipulate this equation. Jesse? Haley? And divide by R. So you're trying to, what in general are you trying to do? Solve for K. So get the K over to the side, put all the other junk over to the right. All right, do it. Solve for K. Get K on one side, all the rest of the junk on the other side. got? What form did we put that equation into? Slope-intercept form. Okay. What does this chunk mean? TC over R. It's what? The intercept. What does it mean though? So that's definitely the intercept. I totally agree with you. What does it mean kind of in economic terms? No, it's not a change. So it's the intercept. So right over here is TC over R. So for the average total cost, we'd have the total cost maybe we're spending on capital divided by the units of capital. But here we've got maybe we've got $100 to spend, and the rental rate for this piece of machinery is 20 bucks. Labor equals 0, right? So we're spending all of our money, all of our cost, all of our spending has been devoted to capital. So that's what that endpoint is. Good. So I'm glad you brought up labor 0. So think about all money spent, all expenditure is on capital at that endpoint. All right, and hopefully we got that the slope of this thing is negative W over R equals negative W over R. Is this looking kind of familiar, by the way? Kind of got that feel of the budget constraint that you need to know for Wednesday? Same type of problem. So now we've got the slope as the wage rate over the rental rate. So again, to tell the story there, well, you tell me, first of all, who wants to give me a stab at what that story would be? Suppose that the wage is equal to 10 bucks and the rental rate's equal to 20. What is that saying in economic terms? Yeah, that's definitely the price of goods. I want to translate it back to the quantities to give you a little bit of a hint. And this one, Jesse, has the changes. We want to think about the rate of change because it's a slope. Why don't you do it? Plug in the numbers. Tell me what you come up with. What'd you get? Okay, so don't use the word wage, but yes, you got the right lingo going here. For every one what, you get what? To labor, right? So we start to see the quantities that I can trade depending on, for my eraser production, if I want a more capital intensive method or a labor intensive method, now I know that I can get 2 units of labor for every 1 unit of capital at the current market rates for these resources. So when we do the math here, same trick that we did with the budget constraint, the wage rate is the dollar amount per unit of labor. The rental rate is the dollars per unit of capital, which gives us the number of units of capital that can be traded for each unit of labor. In this case, it was a half. So I guess this works here. We get 1/2 of a unit of capital for each unit of labor. That's the trade-off. Or as you stated it, you could say 2 units of labor for every 1 unit of capital. Okay? So it's giving us that ability to trade resources, kind of the trade-off that the market allows us to do.
So when you're comparing labor and capital, like, you know, manual labor versus a machine doing work, do you just have to assume all other things constant? You know, like try to take the human error out of it?
No, you'd want the human error embodied in it if you can, which might be difficult, but you might have a that type of factor built into it. So if labor was a machine, they could in theory do 100 units per hour, but because they're not, maybe they only do 90 or something. You see what I mean? You could take that error into account. For these problems, of course, it'll be very mechanical.
Yeah.
The labor will be treated like a lump of coal. You add another person, you get 10 more units, you know, that type of thing. But in the real world, yes, you'd have a heterogeneous labor force with various skills and various abilities and all of that stuff. Okay, any other comments or questions there? All right, so the flip side of the equation is this quantity part. How do quantities get made, and what's the relationship between quantities and resource levels? So next, let's put the relationship between quantity and labor and capital. So quantity of output is some function of labor and capital. We can get more fancy and add in, of course, other resources. And we can also add in like a technology parameter that allows that function to morph. But in its most general form, for now anyway, for starters, let's think about output being determined by so many people, so many capital. The one thing that's important to note is that there's no prices in here. There's no wages, there's no rates. This is a engineering concept, right? How do I build this? I don't care what it costs. Well, you can use this big old machine and 5 people, or maybe it's possible to use the smaller machine with only 3 people, right? So there's different maps, engineering blueprints that can be used to make that stuff. All right. So we learned about a law in principles class. The law of diminishing. Anybody remember? Related to this concept? It was a diminishing something or other. We had the law of diminishing marginal utility in the chapter with 4 and 5.
For diminishing marginal cost.
No. It's related to that. Return, yes, or product. So it's close, though, to the cost concept. So the law of diminishing marginal product, the law of diminishing marginal product or returns is fine. Those are used interchangeably. The law of diminishing returns or the law of diminishing marginal product states that as you add more and more of a variable resource like labor, it's generally the one that we tend to think of being variable, at least in the short run. As you add more and more of a variable resource like labor to at least one fixed resource, like capital. The amount of product from additional units of labor eventually diminishes or falls. Now, since Adam brought it up, maybe we'll just insert, I probably wouldn't have inserted this here at this point, but it's a good spot to bring it in. This concept gives rise to the law of increasing cost. So costs are going up at the margin because productivity is falling at the margin, causing your average cost per unit to go up. So let's just put a little note. This causes increasing costs at the margin. In other words, an upward sloping marginal cost curve. Upward sloping marginal cost curve. Does that make sense, Adam? Okay, so what does that look like graphically? So graphically, if we now draw labor on the horizontal axis, but quantity of output on the vertical. So notice that. Is this function going to be an increasing function or a decreasing function? Careful. Total product. You're right, and you might have been looking at the marginal product. The marginal product curve would be decreasing. But what is the total product? What does this function look like? The total product. As I add more labor, what happens to my total amount of erasers? Does it go up? So it's going up. It's an increasing function. And what does it look like? Does it look like A, B, or C? C, right? Because of the law of diminishing marginal product. Now this whole concept should start to feel strangely familiar because that's what our utility function looks like, right? So some definite similarities. Now I'll go ahead and add this little curly Q in here. So I'm going to put this little part in here. I'm going to make it go up, but then do this. So this is a general form of a possible production function. And I kind of hesitated a little bit, but we really shouldn't rule this out of what's going on here. And that is possibly some increasing returns at early amounts of the combinations. So as I put a little bit of labor together with capital, extra people could be more productive together than they are independent of each other. So imagine two people, they can specialize in what they're doing instead of one person having to run around. One person can stay at that end of the shop and the other person can stay here, and they can work on different things rather than one person having to run to one side and do two things, right? So there could be some synergies of two people working together, or three people, but eventually the fourth person, the fifth person, the sixth person, the seventh person, the eighth person, eventually the law of diminishing marginal product kicks in. So that's the way that would look like in kind of in functional form here. So at this transition point where this thing quits going up, instead of increasing at an increasing rate, it starts increasing at a decreasing rate. That is where the law of diminishing marginal product kicks in. All right. So now it gets a little more interesting if we imagine if we have what this thing looks like three-dimensionally if we had a capital axis. You know, what does that function look like? Well, if we come over here and we're measuring erasers on the vertical axis, labor's running along this axis, capital's running along this axis, this function's going to come up and over you guys like a big canopy, a big cape, kind of coming up and over us. If I do my samurai sword chop at 100 erasers and I cut through the function and I drop it straight down to the floor so that I'm living in the LK space, the two-dimensional space of labor and capital, guess what it looks like? So imagine this curvy thing coming up and over us, kind of a nice big curved canopy cape. I cut it. Remember, it's increasing, so as I go, it's kind of heading this direction over us. I cut it. I take that slice of the cape, drop it straight to the floor. What does it look like? It looks like that indifference curve. It's going to be a slice that's convex to the origin, holding output now fixed at 100 erasers. Awfully darn close to the concept of our indifference curves and utility. So this now is called an isoquant. An isoquant. Iso, what do you think that means? One, same, right? So same quantity along this curve. Anywhere along this curve, the quantity is the same. And so, come on in, Max. So at point A, B, and C, I'm producing 100 erasers. Point A represents a more capital-intensive production process. Point C represents a more labor-intensive production process. Two ways of producing the same amount of stuff. Which one do I pick? Whichever one best fits the budget, whichever one's the least costly, right? Back to the problem we started with at the beginning. I'm going to choose the cost minimizing method of doing that level of production. The cost of labor and capital is going to affect the what of the iso cost curve that we drew earlier? The slope. And now, as I minimize costs subject to a fixed quantity, what would I be doing conceptually if I start here, because the slope of this golf club now represents the wage to rental rate ratio? What represents less cost than what I have? What happens to the golf club? It shifts. In what fashion? Inward and, is it tilted shift? As we shift it, does it get a little steeper, a little flatter? What makes it steeper or flatter?
Elasticity.
Nope. The prices, right? Because the slope of the golf club here was the wage rate over the rental rate, so the relative price ratio. So if now we're minimizing total cost, it's going to shift inward in a parallel fashion, right? It's not going to rotate at all. And so I'm going to continue to minimize costs subject to this constraint until the ISO cost curve is just kissing 1 point on the Isoquant. One and one only point right here. Turned out to be point D, apparently, with the wage rate and rental rate that I chose. So there is a ISO cost curve right there. There's another one there. There's another one there. There's another one there. There's another one there. But if my objective is to minimize costs subject to producing 100 erasers, I'm going to choose to hire this many units of capital and this many units of labor. Eerily, I'm not doing too good with my pronunciation, eerily similar to our utility maximization problem, right? It's the same thing. And that's what I told you we were going to get into this time, that this would be good review for you for the upcoming chapter, because it's really applying the exact same logic to the firm now in terms of these isoquants and iso cost curves. So, minimizing cost, minimize cost means that we're shifting this inward for a given quantity. So this conceptually describes what I started this whole thing off with.
So the point at which you could solve for would be minimizing the isoquants.
Yes, and that would be the condition now. So the condition that must hold for profit maximization, which, by the way, ties back to marginal revenue equals marginal cost. It's just characterized a little differently here. So the profit maximizing condition for minimizing cost subject to a quantity constraint, which is the problem I presented earlier and we walked through. The condition that must hold is that the slope of the isoquant must be equal to the slope of the iso cost. The slope of the iso cost curve was the wage rate and the rental rate. The slope of the isoquant we haven't talked about yet. We did a little bit, but not specifically the slope of it. But you tell me what the slope of the indifference curve was. So this is beer and pizza now. What was the slope of the indifference curve at a given point? Marginal rate of substitution of beer and pizza, and more specifically that was, no, that was the condition, but break down the marginal rate of substitution. What is the actual marginal rate of substitution? The ratio of what? Sounds like you got to know this better for next week. I think you know it. Be brave, be courageous. It's okay to be wrong. Some of our greatest victories in life come from our
Value
failures.
you put on pizza versus value you put on beer.
Yes, and how do we measure that value? What's it called? Give me the more
Udals?
specific name. Udals, or I don't really like the word udals, but technically Max is right. I think they do refer it, in here they refer it to udals too. I try to avoid that just because I think it's too weird. We do enough weird things in econ class, we don't need an even more weird thing. But you're right, what's the udal in this case? So the value placed by the consumer on beer and pizza, more specific though. It is related to a udal, but let's not go there.
Alright, so that's out of the room this time.
Come on. So what you were saying, this is price of beer over price of pizza. This is correct, but this has more meat to it. What is this equal to? No. It's the ratio of something that you definitely need to know desperately for next week on Wednesday. You guys are just dead meat if you don't know this part. So flip back through your notes and just get my nerves down and my anxiety levels up a little bit. Yes! Gosh darn it. Marginal utility of beer over the marginal utility of pizza. The ratio of the marginal utilities. Now, I was trying to give you something simple so that you could tie this back to something a little bit more unknown at this point, because we just haven't covered it. The slope of the isoquant. What do you figure that is? If this is the marginal what? Marginal product. Good. The ratio of the marginal products. Good, Jesse. I won't have a heart attack today. So we take the marginal product of labor over the marginal product of capital. All right, so now we're on to something. And that gives us what we call, I wanted to get the right acronym, some textbooks use it a little differently, the marginal rate of technical substitution of labor for capital. The MRTS instead of the MRS. The marginal rate of technical substitution. That comes from our production function. So again, marginal product has nothing to do with prices. It's an engineering concept. If I hold capital constant and add another unit of labor, how many more erasers do I get? If I hold the amount of labor constant and add another machine, how many more erasers do I get, right? So the marginal rate of technical substitution gives us that. All right, so now that we're out of time, I thought we were going to get to our first problem there, but we will do that on Monday.
I got a question.
Okay, go for it. Yep.
So are we behind schedule